Our next speaker is Volkan Cevher.
Everybody. All right. So my talk is a little bit more computational, although I'll touch upon some statistical aspects at the very end. So today I'll talk about composite self-concordant minimization. Let me first begin by talking about what I mean by composite minimization, which is a very basic problem. And in fact, I think I'm preaching to the choir here. So suppose we would like to minimize a function phi of x, which is a composition of two terms. In the canonical setting of composite minimization, these two terms, f of x, you assume it's smooth, and the second term is actually, you typically assume it's non-smooth. And this has many applications, and in fact, the applications are growing in signal processing, machine learning, statistical communities. You can think of f of x is your basically square loss, and g of x to be your L1 norm, your nuclear norm, or any indicator function. So the assumption here is that both functions are closed and convex. And this has actually a lot of applications beyond just lasso. It permeates into things like graphical model learning, in scientific imaging, things like post-on imaging, low-rank recovery, and you also seen some talks yesterday about like atomic norm denoising, things like this. And as the way things are going in all of these applications, we are actually in need of algorithms that needs to scale well because we're basically inundated with a lot of data. And in order to respond in some reasonable time to the amount of data we have, algorithms somehow needs to cope up with this growth of the data. Now, this particular form is actually quite interesting and has been the focus of a lot of optimization work. And it has a specific structure which is really suited to splitting methods and augmented Lagrangian methods. But these methods typically do not assume anything about the smoothness of these things. And in the case that I'm interested in, when f of x is smooth, these accelerated proximal methods tends to be better. So when you look at these particular class of methods, they basically rely on two key assumptions. The first assumption is, of course, the smoothness of the function f. And what we basically invariably do in all of these scalable algorithms is that we assume f has Lipschitz continuous gradient. And what that means is if you look at the gradient at 2 points, you look at the norm, it doesn't grow larger than the difference times a constant L, right? And there are certain cases where the smooth function is also strongly convex, so it has a nice quadratic lower bound, and that's like the nicest thing you can ever have because things become much nicer to play with. The second assumption is, of course, the assumption that G is somehow prox regular. It's easy to calculate the prox, and here is the definition of the prox. You have a quadratic term like the proximal point, G of x, and somehow solving this problem we assume is computationally easy or tractable. Now, once you're in this particular region, and in fact, if you're in this cross-section of these two classes, this is a well-understood domain, and you have lots of scalable algorithms that are provably fast, and you have many different schemes, right? But once you step out of these domains, and in particular, if you step out of this Lipschitz gradient domain, the scalability is not great. You typically step out of these and you just start talking about the interior point method and not being scalable, just because what they tend to do is, they take the problem, they lift problem dimensions, they accommodate for the non-smooth terms, they introduce auxiliary constraints, and then they use the standard path following techniques to solve the problem, right? And the issue here is that you just lost all these scalable first order methods, quasi-Newton methods, and so on and so forth. What I will do today is I'm going to talk about yet another popular problem class, which is actually used in the interior point methods. It's an assumption on the smooth function f being self-concordant. How many of you heard about the term self-concordant? Very sparse of you, right? So self-concordant is actually quite popular, especially in the interior point method. All that is I'm going to explain very briefly. If you take your function f, you'd anchor a point x, and then you look at any direction. Along a line in any direction, the function, the third derivative, should be bounded somehow by this particular weird expression with the second derivative. So just tells you how smooth the function is varying. The particular form is not that important. Well, it turns out that the self-concordance happens in a lot of applications. One application is this graph learning problem where suppose you observe some data from a Markov random field, and if you would like to learn the graph structure underlying the Markov random field, you can cast it as this, when you use a log likelihood formulation, you can cast it as a log dead problem with an L1 regularizer. And this particular term is actually not Lipschitz, and it's not strongly convex either. You can also just write a lot of problems that are familiar to you. Like one example is the Poisson imaging problem, which is very popular in the scientific community. There are other problems like you can take lasso and you can assume an unknown variance, and then you try to learn the variance while you're trying to do regression. Things like this, they just spit out these self-concordant terms. And what we've done so far is just three things, and I'll try to highlight as much as I can. So we come up with a variable metric framework to do optimization on, and this is what I will focus on today. The second thing is we have some convergence and some consistency theory, and I'll just briefly touch upon this. And we have a nice software package called SCOP, which will be available next week. All right, so what do you do with composite optimization? I'll just tell you what the basic idea is. The basic idea is as follows. Suppose you have a function f. What you do is, using this Lipschitz gradient assumption, you come up with an upper surrogate. And the upper surrogate is basically, at any given point, is something very simple. It's a basic quadratic. And the idea of majorization, minimization is right here. It's very basic. But as opposed to just minimizing f, you add the g in there, and you try to minimize this expression. And this is precisely this prox term, which we assume to be easy to calculate, quote unquote. And given this, and given this particular problem structure, you can actually prove that this particular scheme has a nice convergence guarantee. Right? You can accelerate this, or you can make this somewhat linear if you have strong convexity. And the idea about the variable metric framework is that, as opposed to just taking a basic quadratic, you try to take a weighted quadratic that better matches the smooth function at a given point. So it's like a tighter quadratic surrogate to it. And the idea about the variable metric is that it gives you a little bit additional computational and accuracy trade-off. So if you use things like BFGS updates, you get, for example, superlinear convergence. And generally, if you satisfy Dennis-Moore condition, or if you actually put just a Hessian there, then you can have like quadratic convergence, which is also quite nice. Right? All right. So what do we do with the self-concordant composite framework? It's business as usual. You take somebody else's framework and you claim it as your own, right? So what you do is, you take an x, you pick a direction, and then you take a step along that direction. So you don't take the gradient directly, but you actually solve a proximal problem to get the gradient. And here, this variable metric literally comes into this term right here, all right? Now, for the rest of the presentation, I'm going to assume this variable metric is just a Hessian. It's relatively straightforward to do this with diagonal metrics, but this is more elementary. The thing I would like to highlight here is that this particular problem, aside from, so if G is like the L1 norm, this is like the unconstrained lasso problem. But one thing to highlight here is that this problem is actually strongly convex because you're using a variable metric which is positive semi-definite. So you have lots of algorithms that solve this really rapidly. And what we've actually done is, so we took this framework and we actually have an analytic way of calculating what the step size is. That's why we call it our framework, right? So what do we do? Well, this is one of the densest slides I probably ever made, but just bear with me. I'm assuming this crowd can do background subtraction. So these are the equations you get for this Lipschitz gradient and strongly convex functions. You have a nice upper and lower surrogates to the function given the bounds on the Hessian. The thing with the self-concordant function is quite similar. You have one-to-one correspondence with these, except that your Hessian upper and lower bounds change. They're a little bit more complicated. They're more local. They're matched to the local structure more than the global structure. And the functions also, the surrogates you also get are somewhat local. In fact, the upper surrogate is local. Now, this makes it a little bit more difficult to actually, analytically derive certain things, but when you do, the algorithm tends to work better because it's better matched as you're doing local steps to converge, it is better matched to the smooth function. And here, just for the rest of the presentation, I'll start putting these little x's down in a norm, and that's just the local norm where you take, for example, you transpose the Hessian of the matrix U, right, and the dual norm is defined the usual way. And you, as opposed to having these quadratics right here, you have some more generalized functions that look like quadratic locally. All right, so what do we do? What you do is very simple for the Hessian, the second order method. In fact, this is very elementary. That's why I chose to highlight it. So if you just take the upper surrogate of the f and you basically use the optimality condition for this direction that you're taking, that you calculate through the proximal step, you'll see that you can come up with a descent equation, which is a function of the step size alpha. Then what you do is, given that the variable metric is this Hessian, you optimize to get the best descent possible, which you can do analytically. And it turns out that you get a nice alpha, which basically you cannot improve given the structural equations. And this is nice, actually, because given this alpha, we can come up with an analytic complexity bound for the convergence of such algorithm for the self-concordant, composite self-concordant optimization. The idea here is that this has more or less two phases. There's one phase where you get into this quadratic convergence region, which we can calculate explicitly. And once you make that calculation, you don't need to calculate any step size. You just set the step size to 1. And when you're out of this quadratic range, you basically have this distance of the objectives divided by a constant. And the cool thing about this is that you can actually accelerate this part significantly, because what we do is we calculate an analytic step size, and we basically enhance all the known step size procedures like Armijo rule, just because we now have a lower bound, structural lower bound at which we can safely take a step, right? So there are many things you can do. If you think about the standard backtracking steps, backtracking line search, you can easily actually go beyond an overjump in terms of your step size, so you can prevent that. Or you can basically start from this particular step size selection procedure and then actually try to go a little bit more greedily. And practically that makes a huge difference, and I'll show it in the context of graphical model selection. So let's take this simple example. We have a log dead term and an L1 norm on a matrix. If you look at this, it's actually a large scale problem, but it has a very nice spatial structure. So if you look at the Hessian of the problem, it actually is a Kronecker product of matrices. So it's actually a huge matrix, but it is a Kronecker product. And you calculate the proximal Newton direction the same way you do, which you solve a proximal problem. But it turns out that as opposed to just doing going through this problem in the primal form very naively, if you look at the dual form, what I showed here is that you only need, turns out that you don't need to, for example, calculate matrix inverses that is necessary to calculate even the gradient. These terms combine in such a way that you end up with a problem that you need to solve, which has the sparse matrix and a smooth minimization. No inversions and no Cholesky decompositions necessary. And here, because we're calculating the step size analytically, you end up coming up with an iterative scheme that solves this self-concordant composite problem on the semi-definite cone without ever doing Cholesky's or matrix inversions, which is kind of nice. And you actually compare this against existing state-of-the-art methods, and you actually do see a significant difference in terms of the number of function evaluations and in terms of the convergence. And we basically tested various step size selection procedures, and we see that the overall computation decreases significantly. And the nice thing about this is that you still have this rigorous convergence guarantee that nobody had before. One of the things about this dual method is that because it just uses matrix multiplications, it makes it very nice to implement in a GPU, right? It's what the GPUs do, just matrix multiplications. Then you make various comparisons, and you see that you can handle large problem sizes very efficiently. All right. The second order method is nice, but you can also apply the first order method to problems like Poisson imaging. So here's one example. You get an image sampled through some low light imaging device. So you end up having a Poisson likelihood, and what you want to do is you want to solve this log likelihood regularized with a TV norm. And the state-of-the-art method is spiral tap. So if you run like R codes in spiral tap, you won't see any difference in the images because both methods converge nicely. The only difference is the time, right? If you run the methods, typically we get on the average 3 times faster, and there are many cases where you can be like, hundreds of times faster, just because spiral tap basically relies on the step size selection procedure, which might fail in certain cases because the parameters that go into this particular problem, like the regularization parameter can be like 10 to the minus 4, things like this. All right, so what we've done actually is we said, hey, this is interesting because you're solving a composite self-concordant problem, and this actually happens in a lot of applications where you're trying to minimize an objective subject to a convex constraint, right? So what you can do in this particular setting is that if the convex constraint has a barrier formulation, which is self-concordant, you can try to do path following on it. And the idea here is that you try to solve a sequence of problems where you take the self-concordant barrier on this particular set of omega, and you try to update your x estimate. As you're updating, you update your regularization parameter so that in the end you converge to a very close solution to this particular problem, right? This idea is quite nice because when you think about disciplined convex optimization, like what CVX does is it takes a problem and puts it into some canonical form that it just handles with some standard methods. In our case, there's no lifting required. And the issue with lifting is that when you do path following in such problems, what you need to do is you need to do things like Nesterov-Tott scaling, which basically destroys all the known sparse structures within the problem itself. So we basically preserve this. And let me give you one example. So here's this max norm clustering problem where you want to find a clustering matrix K given an incidence matrix A, and the particular form is not that important, but it has a cone constraint and some simple additional constraints. And when you actually put this, typically what people tend to do is they say, okay, we proved the consistency of this particular estimate, we put it into CVX, it doesn't scale well, so we do it this way, and then we apply our splitting method, which is, it's not guaranteed to converge to the global, but it always does well, right? So you take this problem, you see that the things like Sedumi the complexity will grow something like p to the 5 to 5. Here, p is one of the dimensions of the matrix. And if you plug it into our solver, you'll have this nice p cubed kind of scaling, which is proportional to matrix multiplications, which is kind of nice. And when you actually look at the timing, for example, so PF stands for path following our method versus Sedumi and splitting, you'll see that splitting does really well in terms of time. Now, in this particular case, if you actually look at the objective values, you'll see that splitting doesn't even get the first single digit accurately. So this is actually a big Monte Carlo run where we run the algorithms and we record the success of, for example, splitting. And here you'll see if you run splitting, like out of 100 simulations, splitting will do well on 20 of them. But in the rest 80, so by splitting, by the way, for the people who know this, it's just Buer-Montero splitting. You'll see that, for example, the objective value can be significantly different. So many of these cases, solving the original convex problem may be important. And if you're doing that, I think our path following scheme, which doesn't lift the problem, is much more scalable. Another advantage you get is because you're doing path following, you can actually look at the whole sparsity regularization path of like graph learning problems. So if you think about it in graph learning, you have a regularization parameter and you don't know its value, right? One idea is, typically you say, hey, I want, one sparse graph or 2 sparse graph. What you need to do is somehow figure out what that regularization parameter needs to be. In our case, what we do is we literally just pick a regularization parameter and tell the algorithm to go in one direction. And what it'll do is, for example, it'll start with a very sparse solution. It'll just sweep through the whole Pareto frontier of the solutions with no input from the user. It'll do it automatically. All right. So how much time do I have? 5 minutes, perfect. All right. So what we've also done is we looked into some generalization of this self-concordance, because the idea here is that, you know, the more structure we can exploit with the smoothness, the better. Now, there are many applications where you have Lipschitz gradient, but actually it turns out that you can assume more. For example, in logistic regression problems, we know that, for example, the logistic function is Lipschitz gradient. But it turns out that the logistic function also satisfies a little bit of a more generalized form of self-concordance. So here, the assumption we have is something like, okay, so let's take an f, fix an anchor point x in the domain of f, and then just take a look at any direction and look at how the function varies along a line, right? And we assume, you know, this third derivative along the line is some function of the second derivative and the norm of the direction, right? So you can do this for things like, you know, logistic, multinomial logistic, robust regressions with cosine hyperbolic data error. This also happens in conditional random fields and geometric programming. Now, if you take this and just code the simplest gradient method, which we can prove under certain conditions will have linear convergence, and just test it against the fast methods that are coming from the Lipschitz gradient camp, so to say, right? You'll see something very interesting. So here, this is a 70,000 dimensional data, and you have 20,000 samples. You run, for example, the Nesterov method with backtracking step size selection procedure, which has many enhancements. You'll see the sublinear convergence. And if you do the dual prox algorithm, it has a little bit faster convergence, right? You just put the simple basic gradient method, and I'm not putting the faster, the accelerated version of this. Here's the convergence you have. Now you might be thinking, okay, the iteration is not, you know, so impressive gains, but you have to think about what the cost of per iteration for both algorithms is. So here, you're doing dual prox per iteration and some fancy step size selection procedure. Same thing here. And if you compare these in times, this runs in seconds on this huge dimensional, large scale data, and these are much slower. All right. So we also looked into the statistical aspects of this, and it turns out that if you have generalized linear models where you know, the log likelihood actually spits out a self-concordant term, you can do some consistency results. And the key idea here is that, you know, the canonical way of assuming this irrepresentability condition, you can use similar arguments and do very tight consistency bounds. For example, with L1 regularization, you can say when the model you learn will be support consistent. And the cool thing here is that, I mean, you just take the optimality condition, you go for the third derivative in the Taylor series expansion, and you know that it's bounded by the second derivative. So you play this game and give some nice consistency results. All right, so I'll end with this. So what we've done in this particular work is that, you know, we've taken innocuous assumption on the smooth part, self-concordancy, and we basically proposed a variable metric framework, which seems, I mean, as far as I know, this is the one that has the first rigorous convergence guarantees without lifting the problem dimensions. And I mean, the framework itself is not new, but our contribution was this particular step size selection procedure, which turned out to be quite important. And what I've done is I mostly concentrate on the practical contributions, and the package, which is self-concordant optimization package, should be available online next week, and I would be you know, happy to interact with you to see if we can apply it to your application. All right, so I'll end with that. Thank you very much. Spiral tap? Oh yeah, so it turns it up to 11. It is a software package that takes the Poisson log likelihood. It adds an epsilon term in the log term so that it becomes Lipschitz gradient, and uses Barzilai-Borwein step size selection to achieve descent. And it is by Becca Willett.
So I have a question. I think everything you did was unconstrained.
then can you still use your step size selection, or are you
Exactly.
just
So
using
it doesn't matter. If you have a constraint, typically what you do, I mean, if it has a self-concordant barrier, you just put it as a barrier function and you're fine, because that literally feeds into the framework we have. If it's a constraint set that you can project easily, you just put it as an indicator function and you're fine. So like, you know, you can handle it two ways, one path following or the other one as an indicator. And nothing changes. Like the step size selection procedure is invariant. So if you have your group norm with sparsity within the groups and something else, all you need to do in this function is just provide your prox operator. So you can do it with Poisson model, for example. Doesn't matter. It'll do everything automatically.